Picture the universe not as the static, silent expanse we see when we gaze at the night sky, but as a churning, invisible ocean, its surface calm and familiar, but its depths teeming with unseen forces. Right now, as you watch this, an invisible tide is pulling at the edges of galaxies, bending the fabric of reality itself. This is the hidden realm of dark matter and dark energy, the universe's most elusive architects. Together, they make up over 95% of everything that exists, yet they leave no trace we can directly detect. We're sailing blind through a cosmic sea, surrounded by mysteries we're only just beginning to map. Think about that for a moment. Everything you've ever known, every star, every planet, every speck of dust, is just a tiny fraction of what's really out there. The rest, a shadow universe, invisible but undeniably powerful. Dark matter weaves an unseen scaffold, holding galaxies together despite their furious spins, while dark energy stretches the cosmos apart faster and faster, as if space itself has a mind of its own. These aren't just abstract ideas tucked away in textbooks, they're the forces shaping your reality right now, dictating the fate of everything from the smallest atom to the grandest supercluster. And that's where our journey begins. Over the next 25 revelations, we're diving into the heart of these cosmic enigmas, uncovering how scientists hunt what they can't see, why dark energy might one day tear reality apart, and what happens when the rules of physics seem to bend before our eyes. This isn't just a story about distant stars, it's a detective story, a thriller, and a glimpse into the greatest puzzle humanity has ever faced, so buckle up. By the time we're done, the universe and your place in it will look utterly different. If you could gather every star, every planet, and every speck of interstellar dust in the universe and place them on a cosmic scale, they wouldn't even come close to balancing it. The visible universe, everything we can see, touch, or study with telescopes, makes up less than 5% of what's actually out there. The rest, dark matter. Invisible, mysterious, and outweighing ordinary matter by a staggering 5-to-1 ratio. Here's how we know. Picture a spinning galaxy like our Milky Way. Stars on the outer edges should, by all rights, be flung into the void just like water droplets flying off a spinning bicycle wheel. The gravity from the visible mass of stars and gas isn't nearly strong enough to hold them in place. Yet somehow they stay put. The only explanation, an enormous, unseen force, dark matter, acting like an invisible hand, gripping those stars and keeping them from escaping. But the proof doesn't stop there. When astronomers peer at distant galaxies, they sometimes see them warped and twisted, as if viewed through a funhouse mirror. That's gravitational lensing, the bending of light by massive objects. The twist, there's often nothing visible causing the distortion. The math demands something with immense gravity is there, bending space-time itself. Again, dark matter is the silent culprit. Think of it like this. If the universe were a play, ordinary matter would be the actors under the spotlight, visible, dramatic, but fleeting. Dark matter is the stage itself, unseen but holding everything together. It shapes galaxies, guides their motions, and governs the largest structures in existence. And yet, despite its overwhelming dominance, it refuses to interact with light or matter in any way we can directly observe. That's the paradox at the heart of dark matter. It's everywhere, shaping the cosmos at every turn, yet it slips through our detectors like a ghost. We know it's there because without it, the universe as we know it would fly apart. But the harder we search for it, the more elusive it becomes, a cosmic heavyweight hiding in plain sight. The universe isn't just sprinkled with galaxies at random. It's organized like a vast, intricate spiderweb, with threads of dark matter stretching across billions of light years. This invisible scaffolding, known as the cosmic web, is the hidden blueprint behind everything we see. Without it, galaxies would scatter like leaves in the wind, unanchored and disconnected. But thanks to dark matter's gravitational pull, they cling to these colossal filaments like dewdrops on a silken strand. Imagine the universe moments after the Big Bang, a swirling, chaotic soup of energy and matter. As it expanded, tiny fluctuations in density gave dark matter the upper hand. Its gravity acted like a magnet, pulling ordinary matter into its grip. Over billions of years, these patches grew denser, forming a network of threads and nodes where galaxies would eventually bloom. Supercomputer simulations reveal this web in stunning detail. Rivers of dark matter flowing through the void, intersecting at massive knots where galaxy clusters now thrive. You can think of it like a city's subway system. The bustling stations, those bright hubs of light, are the galaxies and clusters we see. But the real infrastructure, the tunnels connecting them, are the dark matter filaments, unseen yet essential. Without them, the cosmic metropolis would collapse into chaos. Even now, this web is still evolving, drawing galaxies closer along its strands while dark energy pushes the empty expanses farther apart. Here's what's even wilder. We're not just observers of this structure, we're part of it. The Milky Way sits along one of these filaments, a single thread in a tapestry larger than our minds can grasp. Every time astronomers map the positions of thousands of galaxies, they're tracing the contours of this hidden architecture. The cosmic web doesn't just shape the universe, it is the universe with dark matter as its silent architect. And somewhere in those uncharted depths, new mysteries are waiting to unravel. For centuries, scientists assumed the universe was expanding like a ball rolling uphill, slowing down under gravity's relentless pull. Then, in 1998, two separate teams of astronomers made a discovery so shocking it flipped cosmology on its head. Instead of slowing, the expansion of the universe was speeding up. Galaxies weren't just drifting apart, they were being flung away from each other faster and faster, as if some invisible force had pressed down on the cosmic accelerator. This revelation earned them the Nobel Prize and introduced the world to dark energy, the most baffling player in the cosmos. To understand just how bizarre this is, imagine blowing up a balloon with tiny dots representing galaxies. At first, the dots move apart steadily as you inflate it. Now picture the balloon suddenly inflating faster on its own, stretching the dots away from each other at an ever-increasing rate. That's dark energy in action. It's not just winning against gravity, it's rewriting the rules of the game. What we once thought was a cosmic tug of war has turned into a one-sided domination, with dark energy pushing the universe toward an increasingly empty, fractured future. The real kicker, we have no idea what dark energy actually is. Einstein once proposed a similar concept, the cosmological constant, but even he dismissed it as his greatest blunder. Now it might be his greatest accidental prediction. Some theories suggest dark energy is a property of space itself, a sort of anti-gravity woven into the fabric of reality. Others argue it could be an entirely new kind of field or particle, something beyond our current physics. What's certain is that it's relentless. While dark matter binds galaxies together, dark energy works in opposition, tearing the cosmic tapestry apart. Here's what keeps cosmologists awake at night. If this acceleration continues, distant galaxies will eventually vanish from view entirely, their light stretched beyond detection. The universe could end not with a bang, but with a whisper, an eerie, frozen isolation where galaxies are so far apart, no future civilization will ever know the cosmos was once brimming with neighbors. Dark energy isn't just shaping the universe, it's erasing it one speeding galaxy at a time, and we're only beginning to grasp the stakes. Long before modern telescopes or supercomputers, a brilliant yet cantankerous astronomer named Fritz Zwicky stared at the Coma cluster, a swarm of galaxies millions of light-years away, and noticed something that shouldn't be possible. The galaxies were moving so fast they should have torn themselves apart. The visible mass in the cluster, all those blazing stars and swirling gas clouds, couldn't possibly generate enough gravity to hold them together. In 1933, with a stroke of insight, Zwicky proposed the unthinkable. There must be something else out there, invisible and mysterious, providing the extra gravitational glue. He called it Dunkel Materie, dark matter. Zwicky was the kind of scientist who thrived on controversy. Colleagues described him as combative, often dismissing rival researchers with colorful insults. He once referred to them as spherical bastards because he claimed they were bastards no matter which angle you viewed them from. But beneath the abrasiveness was a mind razor sharp enough to see what others missed. When he calculated the mass needed to keep the coma cluster intact, the numbers didn't just suggest a small discrepancy, they revealed a gaping hole. The cluster required 400 times more mass than anyone could account for. For decades, Zwicky's radical idea was brushed aside. The scientific community, reluctant to accept an invisible, undetectable substance shaping the cosmos, wrote it off as a quirk of his calculations. But Zwicky, ever the provocateur, doubled down. He even suggested dark matter might someday be found through gravitational lensing, a prediction that wouldn't be confirmed for another 50 years. His contemporaries couldn't have known that this so-called missing mass would later explain everything from galaxy rotations to the cosmic web itself. What's striking isn't just that Zwicky was right, it's how right he was, decades ahead of his time. Today, we take dark matter for granted as a pillar of modern astrophysics. Yet back then, it was the wild hunch of a man many dismissed as difficult, even unhinged. There's a lesson in that. Sometimes the truths that reshape our understanding of reality don't come from consensus. They come from those bold enough to stare into the void and insist, against all ridicule, that the universe is hiding something extraordinary. Zwicky didn't just discover dark matter. He proved that the cosmos always has another secret waiting, if we're brave enough to challenge what we think we know. Let's do a cosmic inventory. If you could take everything in the universe, every galaxy, every black hole, every speck of interstellar dust, and split it into 3 piles, here's what you'd find. The first pile, the one we know best, is ordinary matter, stars, planets, you and me. That pile is pathetically small, just 5% of the total. The second pile, dark matter, is 5 times larger, making up 27%. But the third pile, it dwarfs them all. Dark energy isn't just winning the cosmic popularity contest, it's the overwhelming majority, claiming a staggering 68% of everything that exists. To put that into perspective, imagine the universe is a $100 bill. Visible matter gets $5, dark matter gets $27, dark energy. It pockets $68 and then some. That means everything we've ever observed, studied, or dreamed about, every mountain, every ocean, every distant supernova, is just pocket change compared to the invisible forces pulling the universe's strings. Here's where it gets even stranger. Dark energy isn't just abundant, it's becoming more dominant over time. As the universe expands, the amount of space increases, which means more room for dark energy to exert its influence. Picture a balloon inflating. The more it grows, the more its surface stretches, and the faster the dots on that surface fly apart. That's exactly what's happening on a cosmic scale. Dark energy isn't diluted by expansion like matter or radiation. It thrives on it, growing stronger as the universe gets emptier. So why does this matter? Because dark energy isn't just a passive ingredient in the cosmic recipe, it's the head chef, dictating the universe's ultimate fate. If it continues unchecked, it could lead to a big rip, where galaxies, stars, and even atoms are torn apart by runaway expansion. Or it might settle into a slower, colder demise, leaving the universe a vast, lonely wasteland. Either way, the lesson is clear. The forces we can't see aren't just lurking in the shadows, they're calling the shots, shaping reality on scales we're only beginning to comprehend. And that 5% we call home, it's just along for the ride. Think about the last time you turned off the lights in a pitch-black room. Even when your eyes adjust, there's nothing to see. No shapes, no shadows, just an all-consuming darkness. Now imagine that same emptiness, but on a cosmic scale. Dark matter isn't just hard to spot, it's fundamentally, utterly invisible. Unlike stars that blaze with light or planets that reflect it, dark matter doesn't interact with light in any way. It doesn't glow, it doesn't cast shadows, it doesn't even block the light passing through it. If you could somehow hold a chunk of dark matter in your hand, you'd see right through it as if it weren't there at all. This ghostly quality is what makes dark matter so maddeningly elusive. Ordinary matter, the stuff we're made of, constantly interacts with light. Electrons in atoms absorb and emit photons, giving us everything from the colors of a sunset to the glow of a smartphone screen. But dark matter, it's as if it exists on a parallel plane, completely indifferent to the electromagnetic force that governs our visual world. Scientists have bombarded it with every wavelength imaginable, from radio waves to gamma rays, and it leaves no trace. No signature, no fingerprint. Here's where the cosmic detective work begins. If dark matter won't reveal itself through light, how do we know it's there? Gravity. Picture a crowded dance floor where one dancer moves unseen. You can't spot them directly, but you notice others reacting to their presence, pulled subtly off course. That's how dark matter betrays itself. It tugs on stars, warps galaxies, and bends the very fabric of space-time, leaving gravity as its only calling card. The irony is almost poetic. The same force that keeps your feet on the ground is the only thing that outs this cosmic phantom. Every spiral galaxy's whirlpool arms, every cluster's gravitational lensing, these are the cosmic breadcrumbs leading us toward an invisible truth. And while we've built entire underground laboratories to catch fleeting whispers of dark matter particles, the universe keeps its greatest secret just out of reach, reminding us that some mysteries refuse to be seen. They can only be felt in the silent pull of the unseen. For decades, astronomers assumed the universe's expansion was like a marathon runner gradually slowing down, exhausted by gravity's relentless pull. Then, in the late 1990s, two teams studying distant supernova made a jaw-dropping discovery. The runner wasn't slowing at all. It was sprinting faster, as if some unseen force had kicked it into overdrive. These exploding stars, nature's perfect cosmic yardsticks, revealed something impossible. The universe wasn't just growing, it was accelerating, its galaxies hurtling apart at ever-increasing speeds. The key to this revelation lies in Type 1, a supernova, celestial events so consistent in brightness they're called standard candles. By measuring how dim they appear from Earth, scientists can calculate their distance, and by analyzing their light, determine how fast they're moving away. When researchers compared nearby supernova to those billions of light-years distant, the data painted a bizarre picture. The farther ones were dimmer than expected, meaning the space between us and them had stretched more than predicted. It was like watching a train pull away, expecting it to slow as it climbed a hill, only to see it rocket forward instead. Here's where the metaphor twists. Imagine you're blowing up a balloon with dots representing galaxies. At first, the dots separate steadily as you inflate it. But suddenly, the balloon starts expanding on its own, stretching the dots apart faster and faster. No extra breath required. That's dark energy in action. It's not just countering gravity, it's overriding the universe's brakes, pressing down on the accelerator with no end in sight. The implications rewrite cosmic history. For billions of years, gravity dominated, slowing the expansion from the Big Bang's initial fury. But around 5 billion years ago, dark energy, weak but ever-present, gained the upper hand as the universe grew sparse enough for its repulsive force to take hold. Now it's calling the shots, pushing galaxies apart so violently that light from distant clusters may one day stretch beyond detection, leaving future astronomers with a sky devoid of neighbors. What's truly unsettling is how little we understand this force. Is it a property of space itself, as Einstein's cosmological constant suggested? Or is it something far stranger, a new kind of energy field or particle we've yet to name? Every measurement deepens the mystery. Even the expansion rate, the Hubble constant, doesn't match up between different methods, hinting at gaps in our physics. One thing's certain, the universe isn't just expanding, it's running away from us, and dark energy holds the reins. The hunt for dark matter isn't just about proving it exists, it's about figuring out what kind of cosmic fugitive we're dealing with. Scientists have narrowed it down to two leading suspects: cold dark matter and warm dark matter. The difference: speed. Cold dark matter moves sluggishly, like a ghost drifting through molasses, while warm dark matter zips around faster, though still nowhere near light speed. This distinction might sound technical, but it's the key to understanding why galaxies look the way they do, and why some experiments keep coming up empty-handed. Let's start with cold dark matter, the heavyweight contender. Imagine throwing a handful of marbles onto a trampoline. They'd roll slowly, clumping together under their own weight. That's essentially how cold dark matter behaves. Particles like WIMP, weakly interacting massive particles, move just slowly enough for gravity to gather them into dense halos around galaxies. These halos act like invisible scaffolds, shaping how ordinary matter coalesces into stars and planets. Without them, galaxies as we know them might never have formed. But there's a problem. When supercomputers simulate the universe using only cold dark matter, something's off. The models predict way more small satellite galaxies swirling around giants like the Milky Way than we actually see. It's as if someone pruned the cosmic tree, leaving puzzling gaps in the branches. Enter warm dark matter, sterile neutrinos or lighter particles that move just fast enough to smooth out these inconsistencies. Their extra speed prevents them from clustering too tightly, explaining why we don't find dwarf galaxies everywhere we look. Here's where it gets thrilling. Right now, deep underground in abandoned mines and mountaintop observatories, experiments are racing to catch these elusive particles in action. Cold dark matter hunters use ultra-sensitive detectors filled with liquid xenon, waiting for a rare collision between a WIMP and an atom. Warm dark matter seekers, on the other hand, scour the skies for bizarre X-ray emissions that could betray sterile neutrinos decaying in distant galaxy clusters. The stakes couldn't be higher. If cold dark matter is real, it means the universe's structure was built by slow, patient giants. If warm dark matter takes the crown, it hints at a cosmos shaped by quicker, more elusive phantoms. Either way, the answer won't just solve a scientific puzzle, it'll rewrite the story of how everything, including us, came to be. And with every passing year, the net tightens, bringing us closer to unmasking the universe's most enigmatic architect. Einstein once scribbled a term into his equations: lambda, a fudge factor he called his greatest blunder. Little did he know that very term might hold the key to dark energy. Here's how it happened. In 1917, wrestling with his theory of general relativity, Einstein needed the universe to stand still. The equations insisted it should either expand or collapse, but astronomers at the time believed the cosmos was static. So he invented lambda, a repulsive force to balance gravity's pull, keeping the universe eternally unchanging. When Edwin Hubble later proved the universe was expanding, Einstein dismissed lambda as unnecessary, even embarrassing. But the twist: lambda never really went away. Decades later, when astronomers discovered cosmic acceleration, they realized Einstein's blunder might have been a stroke of genius after all. Today, lambda is the leading candidate for dark energy, mathematically elegant, a constant energy density woven into space itself. Imagine the vacuum of space isn't truly empty but seething with quantum fluctuations, particles popping in and out of existence. This quantum foam could generate a repulsive force pushing space apart. Lambda fits the data beautifully, requiring no new physics, just Einstein's own equations dusted off and repurposed. There's just one colossal snag: the numbers don't add up. When physicists calculate how much energy the quantum vacuum should contribute, they get a value 10 to the power of 120 times larger than what dark energy observations show. That's a 1 followed by 120 zeros, the worst mismatch in science history. It's like predicting a gentle breeze but measuring a hurricane capable of shredding the universe. So where does that leave us? Either our understanding of quantum mechanics is catastrophically incomplete, or dark energy isn't the cosmological constant at all. Some theorists argue lambda might evolve over time, stronger in the past or future. Others propose entirely new fields like quintessence, a dynamic energy that ebbs and flows. But for now, lambda remains the simplest explanation, a cosmic placeholder reminding us that even Einstein's mistakes might point to truths deeper than he ever imagined. The irony is delicious. The term he crossed out could be the very thing holding his legacy together. Galaxies should be cosmic demolition derbies, spiraling whirlpools of stars where the outer edges fling into space like sparks from a grinding wheel. Without an invisible hand holding them together, the laws of physics demand chaos. That's the startling truth Vera Rubin uncovered in the 1970s when she meticulously mapped the rotation of spiral galaxies. The farther a star is from a galaxy's center, the faster it should orbit, just like planets slowing down as they distance from the sun. But Rubin's observations revealed something that defied Newton's gravity. Stars at the edges were whipping around just as fast as those near the core, as if the entire galaxy were a rigid merry-go-round. To grasp how bizarre this is, imagine spinning a pizza dough in the air. The outer edges stretch thin, moving faster than the dense center. Now picture that dough spinning perfectly flat, with the outer crust keeping pace with the inner cheese. That's what galaxies do, except there's no cosmic chef kneading them. The only explanation, an enormous, unseen mass enveloping each galaxy, its gravity anchoring those speeding outer stars. That's dark matter's signature, a gravitational scaffold 10 times more massive than all the visible stars and gas combined. Supercomputer simulations paint an even starker picture. Without dark matter's halo, galaxies spin themselves apart in mere cosmic moments. Stars catapult into the void like stones from a slingshot, leaving behind skeletal spirals stripped of their arms. The Milky Way's outer stars, circling at over 500,000 miles per hour, would have sailed into intergalactic space billions of years ago without this hidden anchor. Rubin's work didn't just prove dark matter existed, it revealed how quietly it shapes the universe. While telescopes show us the glittering facade of galaxies, her data exposed the silent partner behind the curtain, holding the cosmos together against its own furious momentum. Every spiral galaxy's flawless spin is a whisper of that partnership, a reminder that what we see is just the surface of a far deeper, darker reality. We've known about the 4 fundamental forces for centuries: gravity tethering planets to stars, electromagnetism binding atoms into molecules, and the strong and weak nuclear forces holding nuclei together or tearing them apart. But what if there's a 5th player on the cosmic stage, one so subtle we've only just glimpsed its fingerprints? That's the radical idea behind dark energy, not just some passive backdrop to the universe, but an active, repulsive force rewriting the rules of physics as we know them. Picture this: gravity is the quiet giant, always pulling, drawing matter together in an endless tug of war. Dark energy is its mysterious counterpart, a cosmic pusher working in reverse. Unlike the other forces, which weaken with distance, this one grows stronger as space expands. It's as if the vacuum of space itself has a kind of tension, a spring-loaded energy that stretches tighter the more it's pulled. Some theories suggest it's not even constant, that dark energy could fluctuate over time, surging and fading like the tide. This idea, called quintessence, imagines dark energy as a dynamic field, shifting in strength and possibly even switching between attraction and repulsion across billions of years. Here's where it gets wild. If dark energy is a fifth force, it would be the only one that doesn't originate from particles. Gravity emerges from the curvature of space-time, the others from quantum fields, but dark energy might be something else entirely, a property woven into the fabric of existence itself. Some models propose it's tied to an undiscovered particle, a cosmic chameleon that changes its behavior based on the surrounding density of matter. Others argue it could be a sign of extra dimensions, with gravity leaking into hidden realms we can't perceive. The implications are staggering. A dynamic dark energy could mean the universe's fate isn't set in stone. Maybe it's growing stronger now, but in another epoch it might weaken, allowing gravity to claw back control. Or perhaps it's done this dance before, cycling between expansion and contraction in a rhythm we're only now beginning to sense. One thing's certain: if dark energy is a true fifth force, it's the most enigmatic one yet, an invisible hand not just shaping the cosmos but actively rewriting its destiny. And that means the universe's story might be far stranger and far more fluid than we ever dreamed. What if dark matter isn't made of exotic particles at all, but something far more sinister: black holes born in the chaos of the Big Bang itself? This audacious theory suggests that the universe's missing mass could be lurking in the form of primordial black holes, ancient relics forged when the cosmos was less than a second old. Unlike the black holes we know, stellar graveyards formed from collapsed stars, these would be cosmic fossils, remnants of a time when space was so dense and turbulent that pockets of matter could crumple under their own weight. The idea isn't new. In the 1970s, Stephen Hawking and others toyed with the notion that the early universe might have birthed black holes of all sizes, from microscopic specks to colossal giants. But it gained fresh traction in 2016, when LIGO detected gravitational waves from merging black holes with masses around 30 times that of our Sun, far heavier than typical stellar collisions should produce. Could these be primordial survivors drifting through the cosmos for billions of years before finally colliding? Here's the tantalizing part: primordial black holes wouldn't behave like dark matter particles. Instead of diffuse halos, they'd clump in unpredictable ways, warping spacetime as they pass. Imagine a swarm of invisible wrecking balls rolling through the galaxy, bending light around them like a funhouse mirror. Occasionally, one might pass in front of a star, briefly magnifying its light, an effect called microlensing. Astronomers have searched for these flashes, but the results are maddeningly inconclusive. Too many detections would have confirmed the theory, too few ruled it out. Instead, we're stuck in the Goldilocks zone of maybe. Critics argue that primordial black holes can't account for all dark matter. Their sheer numbers would have disrupted the cosmic microwave background or shredded fragile star clusters. But supporters counter that maybe they're just part of the puzzle, mingling with other dark matter forms. Either way, the possibility forces us to confront a humbling truth. The universe's greatest mysteries might not be made of something new, but something we've known about all along, hiding in plain sight, wearing the guise of the familiar. And if they're out there, these black holes could be cosmic time capsules carrying secrets from the universe's first moments. Some might have evaporated by now, thanks to Hawking radiation, leaving behind faint bursts of energy. Others could be drifting between galaxies, silent and undetectable, their gravity the only clue to their existence. It's a haunting thought that the darkness binding the cosmos together might not be a shadow but a void. A reminder that sometimes the most profound truths are the ones we can't see, can't touch, and may never fully understand. The universe isn't just expanding, it's at war with itself. On one side, gravity, the relentless force that built galaxies and clusters, pulling everything together. On the other, dark energy, the silent rebel pushing space apart with ever-increasing strength. The outcome of this cosmic tug-of-war doesn't just dictate the fate of galaxies, it decides how reality itself will end. And right now, dark energy is winning. Picture the most violent finale imaginable, the Big Rip. As dark energy grows stronger, it doesn't just push galaxies away, it overpowers every force holding matter together. First, galaxy clusters are torn apart, their gravitational bonds shattered. Then individual galaxies unravel, stars flung into the void. Next, solar systems disintegrate, planets ripped from their orbits. Finally, in the last terrifying moments, atoms themselves are shredded, particles torn apart as space-time stretches beyond the breaking point. The universe doesn't fade, it's violently dismantled piece by piece until nothing remains but an infinite, empty void. But there's a colder, quieter alternative: heat death. Here, dark energy's victory is slow and methodical. Expansion never becomes violent enough to tear atoms apart, but it never stops either. Galaxies drift so far apart that their light can no longer reach one another. Stars burn out, black holes evaporate, and the universe becomes a vast, frozen graveyard. Temperatures near absolute zero, and all activity grinds to a halt. It's not an explosion, but an endless exhale, a universe so stretched and diluted that time itself becomes meaningless. Then there's the underdog scenario, the big crunch. Imagine dark energy weakens over time, or gravity somehow gains the upper hand. Expansion slows, halts, then reverses. Galaxies begin rushing back toward each other, space collapsing like a deflating balloon. Temperatures soar as matter is compressed into an inferno, culminating in a singularity, a mirror image of the Big Bang. Some theories suggest this could trigger a new universe, a cyclic rebirth where the whole process starts anew. The chilling truth: we don't know which path we're on. Dark energy's strength could change, or some unseen physics could rewrite the rules entirely. But one thing's certain: the fate of everything, every atom, every memory, every distant star, hangs in the balance of this invisible struggle. And the scariest part, we're just bystanders watching as the universe decides its own destiny. Gaze at a photograph of the night sky, and you'll see stars, galaxies, the occasional planet, bright pinpricks against the void. But beneath that glittering surface lies a hidden skeleton, a blueprint of cosmic architecture we can't see with light alone. Thanks to projects like the Dark Energy Survey, we're finally pulling back the curtain on that invisible framework. Using gravitational lensing, the way massive objects bend light like a funhouse mirror, scientists have constructed staggering maps of dark matter's secret empire, revealing a universe far stranger than we ever imagined. These maps aren't just scientific diagrams, they're cosmic treasure charts. When researchers analyze how light from distant galaxies warps as it passes through the cosmos, they can trace the gravitational fingerprints of dark matter, plotting its distribution across billions of light years. The result: a web of filaments and voids so vast they redefine our understanding of structure itself. Picture the universe as a sponge. The glowing galaxies are just the surface, while the dark matter forms the porous, interconnected framework beneath. Some regions are dense knot superclusters where galaxies swarm like bees around a hive. Others are staggering deserts, voids so empty they span hundreds of millions of light years, devoid of even dark matter's ghostly presence. One of the most jaw-dropping revelations from these maps is how little the visible universe aligns with the real cosmic infrastructure. A galaxy cluster might seem impressive, but it's often just a tiny glittering bauble hanging from a gargantuan dark matter filament. The Great Wall, a massive supercluster stretching over 500 million light-years, isn't the exception, it's the rule. Dark matter weaves these colossal threads, and ordinary matter simply follows its lead, clinging like moss to the surface of an ancient tree. Here's what's even wilder: some voids are so empty they challenge our theories of cosmic evolution. The KBC void, a billion light-year bubble where matter of any kind is bizarrely scarce, shouldn't exist under standard models. Yet there it sits, a cosmic blank spot forcing us to rethink how structure forms. Meanwhile, the dark flow, a mysterious motion of galaxy clusters toward an unseen attractor, hints that dark matter's influence might stretch beyond the observable universe, pulling strings we can't yet trace. What's clear is this: dark matter isn't just sprinkled randomly through space. It's the architect, the engineer, the invisible hand that sculpted everything we know. And with every new map, we're not just charting the unknown, we're uncovering the hidden rules of a game the universe has been playing since the dawn of time. Here's something that defies common sense. Pour a drop of ink into a glass of water, and it spreads out, growing fainter as it disperses. That's how ordinary matter behaves in an expanding universe, particles thinning out, losing density as space stretches. But dark energy, it laughs at the rules. As the universe grows, dark energy's density doesn't dilute. It stays constant, as if the ink refused to fade no matter how much water you added. Think of it like this. Imagine blowing up a balloon covered in dots representing galaxies. Every dot moves apart as the balloon inflates, the space between them growing. Now picture each dot getting lighter, its color weakening with every breath. That's matter diluting, but dark energy isn't the dots. It's the rubber of the balloon itself, and as the balloon expands, the rubber doesn't thin, it just creates more of itself, maintaining the same tension per square inch. Space grows and dark energy's push doesn't weaken, it multiplies. This isn't just a quirk, it's a cosmic game changer. Matter's density drops because its particles are fixed in number, scattered across ever larger volumes. But dark energy seems tied to space itself, generating energy ex nihilo as new space emerges. Every cubic centimeter of nothingness carries the same repulsive kick, whether it's in the void between galaxies or the emptiness inside atoms. The more space expands, the more dark energy there is to drive expansion further, a runaway feedback loop with no end in sight. This explains why dark energy only recently took over the cosmos. For billions of years, matter's gravity dominated, its density high enough to slow expansion. But as the universe grew, matter diluted while dark energy held steady. Around 5 billion years ago, the scales tipped. Dark energy's constant push finally overwhelmed gravity's fading grip. Now it's calling the shots, accelerating expansion with no sign of stopping. The implications are staggering. If dark energy's density increased over time, we'd face a big rip tearing atoms apart. If it decreased, gravity might regain control. But its stubborn constancy points toward a slower, colder fate, a universe expanding forever, galaxies vanishing over the horizon, leaving isolated islands of light in an ever-darkening sea. And yet, for all its dominance, dark energy's unchanging nature remains one of physics' deepest enigmas. Why this exact density? Why this perfect balance? The answer, if there is one, lies hidden in the vacuum of space itself, a riddle written in the fabric of reality. We usually think of dark matter as the ultimate loner, particles that pass through each other like ghosts, indifferent to everything, even their own kind. But what if that's not the whole story? Some corners of the universe hint that dark matter might have a secret social life, interacting in ways we never expected. Take the Bullet Cluster, one of the most violent cosmic collisions ever observed. When two galaxy clusters slammed into each other, their visible gas clouds, hot, glowing plasma, crashed like tidal waves, heating up and slowing down. But the dark matter, it sailed right through the chaos undisturbed, leaving the gas behind like smoke trailing a bullet. This isn't just a curiosity, it's a clue. If dark matter were completely antisocial, its distribution would perfectly mirror the stars and gas. Instead, it's as if the dark matter couldn't care less about the collision, while the ordinary matter got stuck in traffic. But here's where it gets weirder. In other clusters, like Abel 520, dark matter seems to lag behind the galaxies, as if it did feel some friction. These contradictions have led scientists to a wild idea: maybe dark matter isn't just one thing. Maybe some of it does interact, not with light or ordinary matter, but with itself. Picture a hidden dark force, a shadow version of electromagnetism, where dark matter particles exchange their own unseen messengers. They might bump, scatter, or even form dark atoms, all while remaining invisible to us. Computer simulations show that a tiny bit of self-interaction could explain why some dark matter halos are puffier than expected, or why certain dwarf galaxies have cores instead of cusps. It's as if dark matter has its own rules, its own playground, where it occasionally brushes against itself in ways we can only infer from the gravitational aftermath. The implications are staggering. If dark matter interacts even weakly, it could mean an entire dark sector exists: dark photons, dark chemistry, maybe even dark stars. Some theories suggest these particles could emit dark radiation, cooling their halos and changing how galaxies form. Others propose dark matter might clump into exotic structures, like invisible mountains floating between the stars. Right now, experiments are hunting for hints of this shadow sociability. Telescopes scan colliding clusters for telltale separations between matter types, while particle accelerators search for anomalies that might betray dark forces. The puzzle is far from solved, but one thing's clear: dark matter might not be the solitary hermit we thought. It could be part of a hidden community, playing by its own rules in a universe within the universe, one we're only beginning to sense. To truly grasp the secrets of dark matter and dark energy, we have to travel back in time, not with a time machine, but with light. Specifically, the oldest light in the universe, the cosmic microwave background, or CMB. Picture it as the afterglow of the Big Bang, a faint whisper of radiation that has been traveling for over 13 billion years, carrying with it the blueprint of the cosmos in its infancy. When scientists scrutinize this ancient light, they're not just looking at a relic, they're reading a cosmic fingerprint, one etched by dark matter and dark energy in the universe's earliest moments. The magic lies in the patterns. The CMB isn't perfectly uniform, it's speckled with tiny temperature variations, hotter and colder spots no larger than a few millionths of a degree. These fluctuations are like cosmic breadcrumbs, tracing where matter clumped together in the dense, searing plasma of the young universe. But here's the twist: the way those spots are distributed, their size and spacing, doesn't just depend on ordinary matter. Dark matter's gravity sculpted them, pulling matter into denser regions, while dark energy subtly influenced how those structures stretched over time. It's as if the CMB is a frozen ripple in a pond, and the ripple's shapes reveal the unseen hands that disturb the water. Enter the Planck satellite, humanity's most precise time machine. Orbiting nearly 1 million miles from Earth, this telescope mapped the CMB with such staggering detail it could detect variations smaller than a galaxy. What it found was a cosmic ledger, a precise accounting of the universe's ingredients: ordinary matter, a mere 4.9%, dark matter, 26.8%, and dark energy, a dominant 68.3%. These numbers aren't rough estimates, they're pinned down with uncertainties of less than 1%, a testament to how finely tuned our measurements have become. But Planck didn't just confirm what we already knew, it deepened the mystery. The data revealed that dark energy's behavior is eerily consistent with Einstein's cosmological constant, a static force woven into space itself. Yet it also left room for tantalizing anomalies, faint deviations that could hint at something more dynamic, like quintessence. Meanwhile, the dark matter distribution suggested it's cold, slow-moving, as predicted, but with wrinkles that still don't quite match simulations. What's astonishing is how much we've decoded from a faint glow in the sky. The CMB is more than a snapshot. It's a Rosetta Stone for the invisible universe, written in the language of temperature and polarization. And as new telescopes probe even finer details, we're not just reading that ancient text, we're adding new chapters to it, uncovering clues that might one day reveal the true nature of the darkness shaping our cosmos. We've always thought of dark energy as a constant force, an unchanging push woven into the fabric of space itself. But what if it's not so steady? What if, like a cosmic tide, its strength ebbs and flows over time? This idea isn't science fiction, it's a serious possibility that could rewrite our understanding of the universe's fate. Imagine dark energy as a dimmer switch, not a fixed setting. In some eras, it might ramp up, accelerating expansion with reckless force. In others, it could fade, letting gravity regain its grip. The consequences would be staggering, a universe that might one day collapse, rip apart, or even oscillate between expansion and contraction in a cycle without end. Enter DESI, the Dark Energy Spectroscopic Instrument, a revolutionary project mapping the cosmos with unprecedented precision. Perched atop a mountain in Arizona, this telescope isn't just snapping pretty pictures of galaxies. It's building a three-dimensional map spanning 11 billion years, measuring the exact positions and velocities of millions of celestial objects. Why? To catch dark energy in the act of changing, by comparing how fast galaxies were moving apart in the distant past versus today, DESI could spot subtle shifts in dark energy's strength, like a detective piecing together a suspect's movements from decades-old footprints. The clues lie in baryon acoustic oscillations, fossilized sound waves from the early universe. These ancient ripples left a predictable pattern in galaxy distributions, a cosmic ruler etched into the fabric of space. If dark energy's push has varied over time, the spacing between galaxies will betray it. Early DESI data already hints at tantalizing anomalies, slight deviations from the expected cosmological constant. Could these be flukes or the first cracks in our model of a static dark energy? Then there's quintessence, the leading alternative. Named after the fifth element of ancient philosophy, this theoretical field could evolve, its energy density shifting as the universe ages. Picture it like a cosmic battery. If it's draining, dark energy might weaken, eventually flipping from repulsive to attractive. A universe that's accelerating now could one day slam into reverse, collapsing in a big crunch. Or if quintessence grows stronger, we might face a big rip sooner than anyone predicted. The stakes couldn't be higher. If dark energy isn't constant, our cosmic forecasts are way off. Everything from the lifespan of galaxies to the very structure of spacetime hangs in the balance. And while DESI is just beginning its hunt, it's already clear. The universe's greatest mystery might not be a fixed force, but a shape-shifting phantom hiding in plain sight. The next decade of data could reveal whether we're riding a runaway expansion with no brakes or if the cosmos has surprises left to unveil. Deep beneath our feet, hidden in the swirling iron heart of Earth, a ghostly secret might lurk. Dark matter, not just drifting through space, but trapped by our planet's gravity, pooling in its core like cosmic sediment. It sounds like science fiction, but physicists are seriously considering this wild possibility. If true, it could rewrite how we understand everything from geothermal energy to earthquakes. Here's how it might work. As Earth orbits the Sun, it plows through the Milky Way's vast halo of dark matter like a ship cutting through fog. Most of these particles would pass right through unaffected. But if dark matter interacts even slightly with ordinary matter, say, through some unknown weak force, Earth's gravity could ensnare a fraction of it, dragging it inward over billions of years. Like sand settling in a jar of water, these particles might accumulate at the planet's center, forming a dense, invisible sphere within the core. The implications are mind-bending. Dark matter collisions could generate heat, subtly boosting Earth's internal temperature. Some researchers speculate this might explain why our planet's core stays molten longer than predicted, like a hidden furnace buried thousands of miles underground. Others wonder if concentrated dark matter could influence seismic waves, creating anomalies in how earthquakes propagate. Imagine, the tremors we feel might carry fingerprints of an invisible cosmic visitor. Then there's the hunt for proof. Experiments like Dharma/Libra in Italy claim to detect an eerie annual oscillation in dark matter signals, peaking every June when Earth moves fastest through the galactic halo, like catching more raindrops when sprinting through a storm. Critics argue these results could be noise, but supporters point to tantalizing correlations in underground detectors worldwide. The debate rages on, with newer projects like Cosine 100 aiming to confirm or debunk the findings once and for all. What's fascinating isn't just the science, it's the audacity of the idea. Our planet, a speck in the cosmos, might not just host life but also hoard one of the universe's greatest mysteries in its depths. And if dark matter truly hides beneath us, it means we're standing atop a vault of cosmic secrets waiting to be uncovered. What if everything we've assumed about dark matter is wrong? There's a radical idea that's been simmering in cosmology for decades, one that doesn't require invisible particles at all. It's called modified Newtonian dynamics, or MUND, and it proposes a startling alternative. Maybe the problem isn't missing matter, but our understanding of gravity itself. MUND's premise is simple yet audacious. Instead of invoking dark matter to explain why stars on the fringes of galaxies orbit faster than Newton's laws predict, it suggests gravity behaves differently at extremely low accelerations, the kind found in the outer reaches of galaxies. Tweaking the math this way can perfectly match the rotation curves we observe. No dark matter needed. Picture gravity not as a rigid rulebook, but as a flexible system that changes its behavior in the cosmic hinterlands, like a car switching to all-wheel drive on slippery terrain. For some galaxies, MUND works brilliantly. Take dwarf galaxies, where dark matter models often struggle to predict their rotation speeds. MUND nails these with eerie precision, as if it's cracked a code dark matter theorists missed. It's a compelling argument why invent invisible particles if adjusting gravity does the trick. But here's where MUND hits a wall. While it excels with individual galaxies, it stumbles catastrophically at larger scales. Galaxy clusters, those sprawling metropolises of thousands of galaxies, contain so much hot gas and visible matter that even MUND-modified gravity can't account for their observed mass. Some clusters would need more unseen mass under MUND than under dark matter theory, an ironic twist for a model designed to eliminate the need for invisible stuff. Then there's the bullet cluster, the cosmic collision we mentioned earlier. When two clusters collide, their dark matter and stars pass through each other while the gas lags behind. MUND can't explain this separation without also invoking some form of dark matter, effectively surrendering its core premise. It's like a detective claiming no crime occurred, only to later admit the suspect might have been involved after all. Critics also point to the cosmic microwave background, that ancient afterglow of the Big Bang. Its intricate patterns align perfectly with dark matter's predictions, while MUND requires convoluted fixes to match the data. Even its creator, physicist Mordechai Milgrom, admits it's more of a description of galaxy rotations than a fundamental theory. So why does dark matter still dominate? Because it's not just about one puzzle, it's about solving dozens at once. From galaxy formation to the cosmic web, dark matter provides a unified framework, while MUND patches one hole only to tear open others. That doesn't mean MUND is worthless. It's a vital reminder that science thrives on dissent, on daring to question even our most cherished assumptions. Perhaps the truth lies somewhere in between, waiting for a deeper theory to bridge the gap. Until then, the cosmos keeps its secrets close, challenging us to think bigger, dig deeper, and stay humble before the mysteries of the dark. Imagine two teams of scientists locked in a high-stakes race, not for fame or glory, but for something far bigger: the fate of the universe itself. In the 1990s, Saul Perlmutter's supernova cosmology project and Brian Schmidt's High-Z supernova search team were working furiously, continents apart, analyzing the same celestial clues: distant supernova, the dying screams of stars. Both groups expected to confirm what everyone assumed, that the universe's expansion was slowing down under gravity's pull. Instead, they stumbled onto a truth so shocking it would rewrite cosmology and earn them the Nobel Prize in 2011. Perlmutter's team struck first, Using the Hubble Space Telescope and painstaking calibrations, they measured Type I, a supernova billions of light years away, expecting their light to reveal a universe gently breaking. The data said otherwise. The supernova were dimmer than they should have been, meaning they were farther away than expected. Space itself was stretching faster over time. At first, Perlmutter assumed a mistake. Maybe interstellar dust was dimming the light, but repeated observations only tightened the anomaly. Across the globe, Schmidt's team, including Adam Rees, hit the same wall independently. As Rees later recalled, "We kept rechecking, thinking this can't be right." The rivalry was intense. Both teams knew the other was close, racing to publish first while double-checking every decimal point. When the results converged, both groups finding undeniable acceleration. It wasn't just a victory for one team over another. It was a paradigm shift. The universe wasn't just expanding, it was doing so at an ever-increasing rate, propelled by something invisible and unstoppable: dark energy. The Nobel Committee's decision to honor both groups in 2011 was a rare moment of unity in a fiercely competitive field. Perlmutter, Schmidt, and Rees became household names in astrophysics, their discovery joining the ranks of Hubble's expanding universe and Penzier's and Wilson's cosmic microwave background. But the real triumph wasn't the prize, it was the humility their findings forced upon science. The universe, it turned out, had been hiding its biggest secret in plain sight, waiting for someone to ask the right question, chase the right anomaly, and dare to believe the impossible. And the craziest part, this was only the beginning. Their work opened a door we're still struggling to walk through, into a cosmos far stranger and far more mysterious than we ever dreamed. Forget everything you know about dark matter being made of bulky, sluggish particles. What if the answer is something almost impossibly light and strange? Enter the action, a hypothetical wisp of a particle so ethereal it makes neutrinos look like sumo wrestlers. Born not from cosmology but from quantum mechanics, actions were first proposed in the 1970s to solve a completely unrelated puzzle: why the strong nuclear force obeys perfect symmetry. But like so many great ideas in physics, this one escaped its cage, becoming a leading contender for dark matter's identity. Picture an action as a ghostly whisper in the quantum realm. Unlike WIMP, which are heavy enough to leave nuclear recoils in detectors, actions would be billions of times lighter than electrons, flitting through space like invisible dandelion seeds. Their absurd lightness means they'd behave more like waves than particles, oscillating at frequencies influenced by magnetic fields. And that's exactly how scientists are hunting them, not with underground tanks of xenon, but with powerful magnets and ultra-sensitive radios. The star player in this search is ADMX, the Action Dark Matter Experiment. Nestled at the University of Washington, it's essentially a high-tech fridge-sized radio tuned to the universe's quietest station. Here's how it works. Inside a supercooled magnet stronger than an MRI, actions, if they exist, should convert into microwave photons under the right conditions. ADMX slowly scans through millions of frequencies, listening for this faint, telltale hum. Think of it like a cosmic metal detector, sweeping through static for the faintest blip of an action's presence. The challenge is mind-bending. Actions could be emitting signals quadrillionths of a watt in power, weaker than a snowflake's landing. To hear that, ADMX must drown out every whisper of heat and electromagnetic noise, operating at near absolute zero. Recent upgrades have made it the most sensitive action hunter ever, probing mass ranges where these phantoms might lurk. Still, silent so far, but in physics, absence isn't failure. Every frequency ruled out narrows the search, like closing doors in a cosmic mansion until only one room remains. What's wild is how actions, if found, would rewrite more than dark matter. They could explain why the universe has so little antimatter, why neutron stars sometimes glow oddly, even why certain quantum symmetries hold true. A single discovery would thread these puzzles together, revealing not just the nature of the invisible cosmos, but the hidden rules governing reality itself. And somewhere in the hum of a magnet's field or the static of a radio void, we might finally hear the universe whispering back. The universe isn't just expanding, it's being hollowed out, stretched into an ever-thinning void by dark energy's relentless push. Picture the Milky Way as a single grain of sand on an infinite beach. The next grain, Andromeda, would sit 60 feet away, but here's the unsettling part: that distance isn't fixed. Every second, dark energy yanks those grains farther apart, accelerating their flight until one day they'll vanish from each other's view entirely. This isn't poetic metaphor, it's the cold, measurable reality of our cosmos. Zoom out further and the numbers become mind-numbing. The average distance between galaxies is now about 10 million light-years and growing. In the time it takes you to watch this video, millions of stars will have crossed an invisible point of no return, their light now too stretched by expanding space to ever reach us. The universe's emptiness isn't passive, it's actively engineered by dark energy, a force that treats the vast cosmic voids not as accidents but as inevitable endpoints. Consider the local void, a region near the Milky Way spanning nearly 200 million light-years of near-total nothingness. Dark energy didn't create this void. Gravity's pull originally sculpted the cosmic web, leaving behind these empty bubbles, but it's turbocharging their growth. As expansion accelerates, these voids swell like lungs, inhaling endlessly, their edges pulling galaxies apart like taffy. Simulations show that in another 100 billion years, all galaxies outside our local group will have receded beyond the observable horizon, their light redshifted into oblivion. The night sky, once studded with distant suns, will go dark to future civilizations, a lonely island in an unseeable sea. The irony is crushing. Dark energy comprises 68% of the universe's energy budget, yet its primary effect is to manufacture emptiness. It's as if the cosmos is a canvas where the paint itself conspires to erase the artwork. And the most haunting question isn't just how this happens, it's why. Why does space itself harbor this repulsive force? Why now, in this cosmic epoch, has it gained dominance? The answers, if they exist, lie in realms of physics we've yet to uncover, hidden in the quantum foam of nothingness or the curled-up dimensions of string theory. For now, we're left with a paradox. The universe grows richer in mysteries even as it becomes poorer in stars. Every galaxy carried beyond the horizon takes with it clues to our origins, leaving behind a silence that stretches faster than light. Dark energy doesn't just shape the cosmos, it's editing the story of the universe, page by vanishing page, and we're here for a fleeting moment to witness the erasure. Beneath the Earth's surface, far from the chaos of cosmic rays and everyday interference, lies a realm of perfect stillness where scientists hunt for shadows. Laboratories like SNOLAB in Canada and Gran Sasso in Italy are buried under miles of rock, their detectors waiting in the dark for the faintest whisper of a dark matter particle colliding with ordinary atoms. Picture these facilities as cosmic listening posts insulated from the universe's noise, where even a single, fleeting interaction could rewrite physics. Building these detectors is an exercise in extreme patience. Take SNOLAB, housed in an active nickel mine 2 kilometers underground. The rock overhead acts like a colossal filter, blocking out nearly all cosmic radiation that could mimic dark matter signals. Inside, scientists work in ultra-clean rooms, their equipment scrubbed of even trace radioactive dust. The detectors themselves are masterpieces of precision. Tanks filled with ultra-pure liquid xenon or argon, rigged with sensors so sensitive they can spot the tiniest flash of light or ripple of charge from a potential collision. It's like trying to hear a pin drop in a hurricane while standing in the eye of the storm. But the universe loves a good prank. For years, the biggest obstacle hasn't been a lack of dark matter. It's been too much noise from mundane sources. Take radon, a radioactive gas that seeps from rocks and even human breath. A single radon atom decaying near a detector can mimic the exact signal scientists are seeking. Teams have spent months painstakingly purging their systems, only to trace contamination back to a researcher's shampoo or a speck of dust carrying ancient uranium. One experiment in Gran Sasso famously blamed a ghost signal on radon wafting from a nearby tunnel, forcing them to line their lab with plastic to block the invisible intruder. Then there are neutrinos, the cosmic tricksters. These lightweight particles flood the Earth by the trillions every second, slipping through rock like it's not even there. While they rarely interact, their faint bumps can look eerily similar to dark matter events. Some experiments now face an ironic hurdle. As detectors grow more sensitive, neutrinos, once background noise, are becoming the dominant false alarm. It's like tuning a radio to hear a distant station, only to realize static from a closer channel keeps drowning it out. Despite the chaos, hope persists. Projects like eludes Zeppelin and Xeno-NNT are pushing sensitivity to unprecedented levels, sifting through billions of collisions to find one that fits dark matter's elusive profile. Every failed search narrows the possibilities like closing doors in a labyrinth. And if a signal ever emerges from the noise, it won't just be a discovery, it'll be a revolution, proof that we've finally touched the invisible hand shaping the cosmos. Until then, the hunt continues in the quiet dark, where science meets patience, and every false alarm is a step closer to the truth. What if dark energy isn't a thing at all, but a cosmic mirage, a trick of the light played by the universe itself? This isn't just wild speculation. A growing chorus of physicists argues we've been misreading the clues, and dark energy might be the universe's greatest feint. The culprit: either gravity isn't behaving how we think, or reality itself isn't what it seems. Take the holographic principle, one of the most mind-bending ideas in theoretical physics. It suggests our three-dimensional universe might be a projection of information encoded on a two-dimensional surface at its edge, like a cosmic version of a hologram on a credit card. If true, dark energy's force could emerge from glitches in this encoding, a side effect of the universe rendering itself into existence. Imagine playing a video game where distant objects move unnaturally fast because the system struggles to render them accurately. That's roughly how dark energy might arise in a holographic cosmos. Proponents like physicist Leonard Susskind argue this could explain cosmic acceleration without invoking mysterious energy at all. Then there's modified gravity, the rebel alternative. Just as Einstein's relativity overhauled Newton's gravity a century ago, theories like massive gravity or tensor vector scalar (TVS) propose new rules for how attraction works across vast distances. In these models, dark energy's repulsive push isn't a substance, it's gravity's own shadow, a mathematical artifact revealing where our equations break down. Picture a sailor blaming sea monsters for strange waves, only to later understand ocean currents. Could dark energy be our own cosmic myth, born from incomplete physics? The stakes couldn't be higher. If dark energy is real, it dictates the universe's fate. But if it's an illusion, it means our grasp of gravity, the force we thought we knew best, is fundamentally flawed. Some theorists, like Nobel laureate Sir Roger Penrose, go further, suggesting dark energy might even hint at cyclical universes, where each Big Bang inherits traces of a previous cosmos. Others explore back reaction, where the lumpiness of the universe's structure locally distorts our measurements, creating the illusion of acceleration where none exists. Here's the beautiful irony: the more precisely we measure dark energy, the more questions it raises. Its density is absurdly fine-tuned. If it were slightly stronger, galaxies would have never formed; slightly weaker, and the universe would have collapsed long ago. Such perfection seems unnatural, almost designed. That's led some to wonder, are we seeing not a force but the universe's way of correcting our assumptions? The debate rages on, but one thing's clear: dark energy's mystery is far from solved. Whether it's a quantum glitch, a gravitational illusion, or a doorway to deeper physics, the answer won't just redefine dark energy, it'll redefine reality itself. And that's the ultimate lesson of cosmology. Sometimes the universe's greatest secrets aren't hidden in the darkness. They're hidden in the light we thought we understood. So there you have it, 25 mind-bending fragments of a cosmic puzzle we're still scrambling to piece together. From the ghostly grip of dark matter sculpting galaxies to dark energy's silent war against gravity itself, every discovery peels back another layer of the universe's grand mystery. What's staggering isn't just how much we've learned, but how much remains hidden in plain sight. Think about it, we're floating on a pale blue dot, surrounded by forces we can't see, tinkering with equations we don't yet fully understand, all while the cosmos expands faster than our theories can keep up. This isn't just astrophysics, it's a humbling reminder of our place in the grand scheme. The atoms that make up your body, the stars overhead, even the screen you're staring at right now, they're just the tip of the cosmic iceberg. The rest, an invisible symphony of dark matter and dark energy, playing out on scales so vast they defy imagination. And yet, here we are, tiny and relentless, decoding the universe one paradox at a time. But here's the thing, the story isn't over. Every telescope pointed at the sky, every particle detector buried underground, every supercomputer simulation is another stitch in the fabric of our understanding. Maybe dark matter will turn out to be primordial black holes. Maybe dark energy will reveal itself as a glitch in gravity's code. Or maybe, just maybe, the next big breakthrough is lurking in a comment below, a spark of curiosity from someone watching this right now. So let's keep the conversation going. Which fact blew your mind the most? Was it the cosmic web's invisible threads, or the way dark energy could one day tear reality apart at the seams? Drop your thoughts in the comments, debate, disagree, or dazzle us with your own cosmic theories. And if you're hungry for more deep dives into the universe's biggest mysteries, hit that subscribe button. The cosmos has plenty more secrets to spill, and we're just getting started.